Etc.
Oh, academic.
Not yet.
Okay. So I was going to say, how did you find that out? But that makes more sense.
There's a thing called the Math Genealogy Project, which is traces your lineage based on who your thesis advisor was. Any questions about anything? So we're going to shift gears today and start talking about complex power series. And so far we've been saying how wonderful analytic functions are. Question? How wonderful analytic functions are in that they're incredibly smooth and well-behaved. And their real and imaginary parts are harmonic and incredibly smooth and well-behaved, etc. Another mind-blowing fact about them is that they're being complex differentiable is going to mean that they're equal to a power series. And nothing like that is true in the real case because there's plenty of real smooth functions that are nowhere equal to a power series. So that's going to be majorly different in the complex case. It's one reason the subject is so different than real analysis. So I've written there, just so you can look at it and say, yep, that sure looks like it's the same definition as if those things were real. But so in this complex case, I want to talk about a series of complex terms, and the sum of that series from 1 to infinity is a limit, means that the usual thing, given an epsilon, then there's an n naught, such that partial sum, I'm going to call these partial sums S sub capital N, minus L, in modulus is less than epsilon when n is greater than n naught. So the main difference is the numbers are complex, and that thing that looks like the absolute value stands for the modulus. And because complex numbers satisfy a triangle inequality, all the basic proofs you find in your freshman calculus book work in the complex case. So I won't be demonstrating those basic facts like the product rule and all those things. So I'll do one of them just to convince you. So an important fact. If the summation an as n goes from 1 to infinity converges, then the terms have to go to 0. That's a one-way implication. You learned that in freshman calculus. So note the reverse is not true. It's not enough for the terms to go to 0 to make something to make a series converge. The classic example is the harmonic sequence. You can study that sum by comparing it to an integral of 1 over x dx, which is the log of x, and the integral test would tell you that sum is infinite, even though the 1 over n's go to 0. As n goes to infinity. Okay, so the proof is a snap, and it's exactly the same as you'll find in a freshman calculus book. Oops. That's right. Sn is the sum as n goes from 1 to capital N, an. The observation is that, and let's suppose that goes to L. as n goes to infinity. And the observation is that a sub n is equal to the nth term minus the previous term, the nth partial sum. So it's the nth partial sum minus the previous partial sums. And those both go to L. So, and this is a rule of limits, that the difference of two limits is the limit of the differences. So this tends to L, and this tends to L. And so the AN tends to 0 as n goes to infinity. So that's all there is to that. So, in particular, if the terms don't go to 0, then the series can't converge. So that's something we're going to use pretty consistently, the corollary. Or just, I guess it's the contrapositive. If AN does not go to 0 as n goes to infinity, this sum from 1 to AN diverges or does not converge. Okay, so the fascinating thing about power series is that there's really only one power series that you need to understand, and it's the geometric series. So let's see. Power series are going to look the same as you saw in freshman calculus, except that the numbers, let's start from 0 power. AN coefficients, which are complex numbers, Z, which is a complex number, and Z naught, which is a complex number. So the ANs are complex, etc. AN and Z naught, Z now are all complex. Okay, and the classic example is the geometric series. Let's write 0 to infinity, z to the n. That's 1 plus z squared plus blah, blah, blah. And when I was messing around with the de Moivre formulas and summing cosine n theta early in the first week of class, I showed you this famous formula. I'll write S sub n. I'll write S sub n of z, since it depends on z now. That would be 1 plus z plus blah, 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 out to z to the capital N. And a famous formula that should be on the tip of your tongue now, because we're going to use it frequently, is that the partial sum is 1 over 1 minus z minus an error. And the error is z to the n plus 1 over 1 minus z. And I like to call this the error. It won't include the minus sign there. I'll call this En of z. And we want to study that error. We expect that probably the limit is going to be 1 over 1 minus z, because we did that in freshman calculus. And of course it is. But you've got to figure out when that is. And to do that, we need to consider the error there. And notice there's a 1 minus z in the denominator. So I'm going to use what I call the denominator estimate. The denominator estimate, I need that denominator to be bigger than or equal to something. if I'm going to bound the arrow from above. And so the denominator estimate is the modulus of 1 minus z is greater than or equal to the modulus of 1 minus the modulus of z. Of course, the modulus of 1 is 1. Okay, and in the numerator estimate, I want a let's see, that'll give me a less than or equal to when I take it upside down in the denominator. And so the numerator estimate is the easy one. The modulus of z to the n plus 1. Because there is no estimate. That's dumb. Okay, so let's do the case. The modulus of z is less than 1. And a very typical thing to do when you're studying power series, let's do a power series trick, is to shrink it a little bit. Let's take modulus of z less than something less than 1. Okay, then that error, en of z, that would be less than, let's see, that's equal to the modulus of z to the n plus 1 over the modulus of 1 minus z. That would be less than or equal to, let's see, when mod z is less than 1, so let's see, that would be less than or equal to mod z to the n plus 1 over, I guess I'll write it like this, 1 minus mod z. I haven't done anything yet. But if mod z is less than 1, then this thing on the bottom is equal to 1 minus mod z. That's a real positive number, so I can take away the absolute value. And so I get here, this thing is equal to mod z to the n plus 1 over 1 minus mod z. So the error is bounded by that. And of course, because mod z is less than 1, since the mod z is less than 1, z to the n plus 1 goes to 0. So we see the series converges for mod z less than 1. And in fact, I'm going to show you it converges uniformly inside the circle of radius r. So the geometric series converges. In fact, it converges to 1 over 1 minus z when mod z is less than 1. And this is an important and it converges uniformly on the disk of radius r about 0 when r is between 0 and 1. No matter how close r is to 1. Because I can further, let's see, I have en of z is less than or equal to z to the n plus 1 over 1 minus mod z. And let's see, if mod z is less than r, then this would be less than or equal to r to the n plus 1 over 1 minus mod z. And let's think about 1 minus mod z. I've got mod z is less than r is less than 1. So minus z is greater than minus r. And so 1 minus mod z is greater than 1 minus r. And now when I take 1 over it, I get 1 over 1 minus mod z is less than 1 over 1 minus r. That's my scratch paper. And so I get this estimate that En of z is less than or equal to this uniform thing that doesn't depend on z, r to the n plus 1 over 1 minus r, when mod z is less than r. And that's exactly what it means to converge uniformly. It doesn't depend on the z. I can get you give me an epsilon, I can give you an n that makes that less than epsilon, and you'll notice there's no z in that estimate. It's independent of z. That's what uniform convergence means on a set. Well, let's think the last case. Any questions about that? So I claim that if you understand that, you understand power series. It'll take me a while to demonstrate exactly what I mean by that, but that's the case. So let's do the case modulus of z bigger than or equal to 1. There's nothing to that case because then the modulus of z to the n, that's the modulus of z to the n, and those would always be greater than or equal to 1 to the n. And so certainly the terms don't go to 0. Series can't converge, so it diverges. Series can't converge. Sounded like that was you-know-who. So this means that the geometric series converges inside the unit disk and only inside the unit disk. So geometric series has a radius of convergence. So the fact is the geometric series has radius of convergence. And in this case, the radius is the radius of an actual circle. In the real case, you might have wondered why the heck we use the word radius. It's because when you go to the complex plane, it's an actual circle of convergence. Capital R is the radius of convergence, and in this case it's 1. That means it converges inside in that circle of radius 1. Whether or not it converges on the actual circle, that's going to be a question, and that's a subtle part. And sometimes it does, and sometimes it doesn't. But it definitely diverges outside the circle. Okay. Let's see. There's some definitions you learned. Let's see. Here's a remark. When you do real power series, let's say, summation as n goes from 0 to infinity, real numbers, Rn x minus x naught to the n. The Rn's real. Then you remember on the real line you had the radius of convergence gave you an interval about x naught. This would be x naught plus the radius of convergence, and this is x naught minus the radius of convergence. And, you got convergence inside this interval between those plus and minus r. But now it's going to turn out that if you let x be a complex number z, you would place x by a complex number z, then you would get convergence on a circle of radius r. See if I can draw a circle. The complex power series would converge inside that circle. So the same series Rn z minus x naught will converge. We're going to show this eventually, soon, on the disk of radius r about the x naught in the complex plane. Well, there's some subtle points that we have to get out of the way about complex series that are very identical to the real case. So in the real case, we talked about absolute convergence. So we'll say that the series of terms, complex numbers, converges absolutely means only that the sum of the absolute, this is not absolute values, these are the sum of the modulus is less than infinity. So that's exactly the same you'd see in your real calculus book. Just that absolute value now stands for modulus. Okay, and one of the most silly sounding theorems is that absolutely convergent series converge. Series that converge absolutely. That sounds pretty dumb. Okay, and if you remember your real analysis proof, so in R, this follows from the completeness of the real numbers. Which means that every Cauchy sequence converges. Well, the complex numbers are complete too. C is complete too, because completeness in the real case implies completeness in the complex case. I won't prove it from scratch, but let me show you how you can prove this fact, knowing the fact for the real case. So we'll call this the proof of that theorem. Let's write un equals xn plus iyn. And then let's see, I've drawn this triangle, this picture before. Let's put here 0. Let's put up here un. That's a complex number. This part right here would be the real part of un. And this part right here would be the imaginary part of un. And this part here would be the modulus of un. That's a right triangle. And so we have the basic estimates that the legs of the triangle, the imaginary part of un, is less than or equal to the modulus of un. And the imaginary part and the real part is all the same. So when I take the real part of the series, so the series summation 1 to n of un is going to be the summation 1 to n of the xn's plus I times the summation from 1 to n of theyn's. And when I take the real part of the right-hand side, so we get, for example, the real part of the partial sum would be the summation from 1 to n xn. And if I take the modulus of that, I would get, I'm going to top out this is the absolute value. The summation 1 to n xn would be less than or equal to the sum from 1 to n absolute value of xn, and that's less than or equal to the sum from 1 to n, the modulus of un. Okay, so if these are less than, if this sum is less, is bounded, in n, that would imply the same thing about the real part. So we see that if the complex series is absolutely convergent, then so that this one is absolutely convergent too. So we're going to assume that this is absolutely convergent. That's going to imply this is absolutely convergent too. And we know the theorem for the xn case. So the real case, fact implies summation xn from 1 to infinity converges. Well, I take the imaginary part and I find out the same thing about the y's. Similarly, the imaginary part. Did I say imaginary above? No, real, yeah. Part shows that the y-ends converge too. And so if both those converge, then of course the limit So it's the sum of the UNs from 1 to infinity would be the real part limit plus I times the imaginary part limit. Okay. I want to show you that the complex exponential power series converges. And the easiest way to do that is with the ratio test. And the ratio test you learned in freshman calculus goes over word for word in the complex case. Once you know that fact about absolute convergence. So the ratio test, we're looking at a sum. Let's start from 0 this time, like power series do. And let's suppose we know that un plus 1 over un converges to some limit L, that'd be a real number, as n goes to infinity. Then you learned in freshman calculus that there's 3 cases. If that L is less than 1, that L is greater or equal to 0, by the way, since those are positive terms. If that limit is less than 1, the series converges absolutely. And you remember in freshman calculus, the way you showed this was by comparing it to the geometric series. And when L is equal to 1, the terms don't go to 0, and so, I'm sorry, when it's equal to 1, the test fails. It could go either way. There's easy examples where it goes either way. But if the case where L is bigger than 1, it's very easy to see that the terms don't go to 0, and therefore the series diverges. The terms get bigger and bigger. That's because the terms don't go to 0. So it's the same old thing as freshman calculus. So the proof is freshman calc. Compare the tail end of the series to a geometric series. And use the estimates we started out with. Read the book for the details of that. To a geometric series. So now we can do a whole bunch of exercises like you did in freshman calculus. For example, what is the radius of convergence of summation as n goes from 0 to infinity, power series, how about n times 3 to the n, z to the n. Okay. Well, if I'm going to use this ratio test thing, I'm going to call this u sub n. And so I need to check the conditions of the ratio test. I look at un plus 1 over un. That would be n plus 1 times 3 to the n plus 1, z to the n plus 1, over n times 3 to the n, z to the n. And that's equal to n plus 1 comes out over n times 3. And then I would have modulus of z. Let me copy that. So now when I use my ratio test, I know that if this is less than 1, I get convergence. Equal 1 fails. Greater than 1 diverges. And so when I put the, let's see, I haven't taken the limit yet. Sorry. That tends, let's see, as n goes to infinity, that tends to 3 mod z. As n goes to infinity. And so we see that that converges if mod z is less than 1. And on the circle of radius 1/3, it fails. I'm sorry, if mod z is less than 1/3. So we see the radius of convergence r, I like to write r of ROC, the radius of convergence, equals capital R equals 1/3. And now for the drum roll, the complex exponential, when you do this business, the complex exponential we're going to see is equal to the famous series you know from freshman calculus, z squared over 2 factorial plus etc. z cubed over 3 factorial plus dot dot dot. Let's see, the general term would be z to the n over n factorial. That's going to be the u sub n. And when I do the routine, un plus 1 over un is going to be z to the n plus 1 over n plus 1 factorial divided by z to the n over n factorial, and that's mod z over n plus 1. And that goes to 0 as n goes to infinity. Of course, 0 is always less than 1. So the series converges for all z. For all z in the complex plane. Of course, it's going to converge. Well, we don't know it converges to e to the z yet, but it does. So maybe I should put in quotes here. We don't know this yet. We're going to demonstrate it soon. So that series is an important one. So it converges for all z. We say that the radius of convergence is infinite. But you might think you can always use the ratio test to analyze a series. And a warning is it doesn't always work. The warning, the ratio test doesn't always work. So you might need something fancier. So let's see an example where it bombs. Let's take a mathy example. Let's let ANs be an enumeration. This is going to feel like Math 341. Be an enumeration of the countable set Remember, that means that it can be put into one-to-one correspondence with the positive integers. The countable set of points in the unit disk with rational, real and imaginary parts. If you want to refresh your memories about countable sets, this is a good thing to think about. You know, the rational numbers in the real line are countable, and the rational numbers, this would be like rational cross rational. And there, remember when you went zigzagging to count that set to see that the rationals cross the rationals is also countable? That was a zigzag counting argument. And then we have a subset of a countable set, and that's countable. So you have to use some facts that you learned in Math 341 to do that, to see that that set's countable. But it is countable. I claim that the sum of a n z to the n has radius of convergence 1. But of course, the ratio test bombs. Because you can't make sense of the an plus 1 over an. They go all over the place. And that's easy to show. Okay. Let's see, maybe this is a good time to... I won't do anything hard for the rest of the hour here. There's a very famous formula. Called Hadamard's formula. French mathematician. There's an actual formula for the radius of convergence. R of summation a n z minus z naught to the n is given by, or I should say satisfies, one over r is equal to the lim sup. You probably heard about lim sups in Math 341. As n goes to infinity of the nth root of the modulus of an. That lim sup always exists as a number. Let's see the case. the case where that limit is infinite, case r equals 0 when that lim sup is infinite. So that case is also true. Let me see, I'll tell you what that lim sup means. Let's think. So what is it? So let's note, what is it? What do these symbols mean? Let's write, let's take the sup of the nth root of an as n, when n is bigger than or equal to capital N. Let's call that R sub capital N. Okay. That set starts for bigger and bigger capital N. So those sets are getting smaller. I'm tossing out elements. These sets get smaller as n increases. I'm tossing out more and more pieces and just looking at the tail end and farther out along the tail end. So these sets, they're getting smaller and smaller. That means the sup is kind of like the max, except it's the max doesn't have to be in the set. Those can only go down. So since those sets are getting smaller and smaller, the RNs can either stay the same or go down. The RNs are they're getting smaller. They're non-increasing. They could stay the same maybe. If I threw out a small one, it would stay the same. If the next one happened to be a big one, it could go down. So they're non-increasing. Sometimes books call that decreasing. And they're bounded below by 0. Let's see, they're non-increasing. And bounded below by 0. And therefore that limit exists. Okay, that exists, and we call it lim sup as n goes to infinity of the nth root of an is equal to, by definition, the limit as capital goes to n goes to infinity of the sup of those terms such that n is bigger than or equal to n. That's the definition of the lim sup. It always exists for sequences of real numbers. The case where that would be infinite, all those sups would be infinite. So you'd have infinite, 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 and of course that's the weird case. But otherwise, if you ever is something finite, then of course it's non-increasing, so it can only go down. Okay, that's a famous formula. I generally try to show it, demonstrate it, but